Okay, then what? Okay, so today we will discuss a new unit. It's about clustering. Okay. Hold on. See waiting room. I needed to admit more. Okay, so it's regarding clustering. Okay. So how do we group similar objects together? Clustering generally, so generally regarding clustering, it's unsupervised learning. Okay, so previously, quite a number of our learning models that we learned are supervised learning. Okay, so this is unsupervised learning because we are going to group them together. Okay, so it's clustering. Okay, so based on the name, it's kind of nature is it to group items together, is it based on similarity. Okay, and there are a couple of ways to do. So today we will learn like a k-means. Okay, so k-means is finding some centers and the items around them. Okay, so that's k-means. And the second approach we are going to discuss is a bottom-up approach. Okay, and it's a hierarchical clustering tree. You will see it's interesting. Okay, and the last one, the third one that we will learn today is called dense-based clustering. Okay, so those are the three ones that we will discuss today. Okay, and the first one is about, the name is called k-means. Okay, it's the k. Okay, the number of k over here, it's the number of clusters. So you need to predetermine, okay, the number of groups, the number of clusters here we said. So that may not be a good choice, the k number, is it? So, but later on we will also learn a couple of approaches to do the justification. Okay, but we need predetermine the number of clusters. So that's called a k-means. Okay, so how the learning algorithm works for the k-means. It's, so you have a number of data, is it? Number of data. So like what I draw is pretty obvious. Is it through group? Is it three group? And so among them, you just randomly pick some centroids. So you pick some samples. Maybe you pick this sample, and this sample as centroid. Centroids. Okay, so for your initial cluster, so here we said we are going to have three clusters, is it? And then based on this, then for each of the sample, okay, you will measure the distance. So this is our centroid, you pick. Then you measure this sample, the distance between this sample and all of these three centroids. So you calculate the distance between them, is it? And then, so this one is closest to this centroid, is it? So you are going to assign this two as one cluster, okay? And then for each of the sample, you're going to do the same thing, is it? You're going to do the same thing. So, but be careful is, after you assign each sample to the nearest centroid, Centroid, is it? The centroid is not going to be a permanent one after you assign it. So it's going to change, is it? So you're also going to move centroid to the sample, is it? So like in these two cases, is it? After this, maybe this one is more central. So then you are going to assign this as new centroid. Okay, so that's the idea. So the centroid, initially you can random pick, okay, but after you assign samples to certain clusters, then your centroid is going to be moved. Okay, so that's the idea over here. Okay, and then next. So that's the general idea about k-means. Okay, so how do we calculate the distance? Is it because you need to measure the sample, the distance between the sample and centroid? Is it one of the distance calculated? We use square Euclidean distance. Okay, so these are the 2 points. Is it 2 sample points? And this is regarding the number of features. Is it? And in math, we know the Euclidean distance, is it? So each component, so over here, each component is each feature, is it? The value between those 2 samples, is it? And find the offset, and then you square and you summation them, is it? So this is called Euclidean distance, okay? And the idea is to minimize, okay, for k-means, is it? We try to minimize what we call it within cluster sum of the square of error. Okay, so that's how do we find the clusters, the cluster. So this is the centroid, is it? So your goal is to minimize the distance, okay, sum of the square of the arrows. Okay, so that's the goal, the predicted one, is it? And the real one, you try to minimize within cluster the sum of the square arrow. Okay, and this expression, the within class sum of the square of arrow, in k-mean, we call it cluster inertia. Okay, later on we will see this. Okay, you calculate this, and then you can also use this as one of the approach to determine the optimal number of clusters. Okay, and then for the cluster centroid, is it pick the initial cluster centroid? What's the smart way? There is a better way than the random pick. You can random pick, is it? And there is a smarter way. We call it k-means plus plus. Okay, so the idea is you have the sample points, is it? Sample point. Then you pick the furthest away point. The furthest away point as the initial centroid. Okay, you're not going to pick the middle one. You pick the furthest away from each other, okay? So that in this way, then it can help you quickly group items together, okay? So this is called k-means plus plus, okay? So keep this in mind also. Okay, and there is also regarding the clustering, we call it a hard clustering or soft clustering. Okay, the k-means we just discussed is considered as a hard clustering because you are going to assign each sample in one of the cluster. Is it in one cluster? So this is called hard clustering. There is another one we call it soft clustering. Soft clustering, it uses a concept called fuzzy. Okay, so in artificial intelligence, is it fuzzy logic? Is it? So fuzzy doesn't mean it's either white or black. Is it? Is either 1 or 0? Is it either this cluster or the other cluster? What it means is it has the probability belong to each cluster. Okay, so that's called a fuzzy. So it has maybe, okay, 80% belong to cluster 1. And another 20% belongs to cluster 2. So it's not a definite one, is it? It's a kind of fuzzy. So that's why we call it fuzzy clustering or soft clustering. Okay, so that's the idea. Okay, and as to the algorithm, we just skip that. And how do we find the optimal number of clusters? Is it with k-means? Is it or k-means plus plus? That's what we learn. One approach is called arable method. Okay, so what does this arable method mean? So arable method will use what we just said, that inertial. Is it that inertial concept? So it's within cluster sum of the square of arrow, is it? And we also call it a name, distortion, is it? So you use that inertial, okay, value, the distribution, and to determine what's the optimum number. So the idea is here you have sum of square of the arrow, is it? And the x-axis is number of clusters, is it? And the arable, is it? It's kind of something looks like this. So this is considered arable, is it? Arable point for the curve, is it? So generally speaking, then this will be the optimal number of clusters, is it? Because after that, the distortion, so this is considered distortion, is it? The distortion rate won't like drop too much, is it? So it's a kind of converge, is it? So this will be a good cluster number. So that's the idea about arable, okay, arable approach. And there is another way, is called we draw some plot, we call it a silhouette plot, okay? And there's some special number we can calculate called silhouette value. And regarding that silhouette, okay, and it also helps to visualize, identify the number of, the optimum number of clusters, okay? And the silhouette is, the value, generally speaking, is bounded in the range of -1 to 1, okay? And normally, if the silhouette value is more approach to 1, then that's a better clustering, okay? And so for a good silhouette, plotting is all of the cluster silhouette value distribution, they will have similar length and width, okay? And if your silhouette plot has visibly different length and width, then it's not a good cluster number, okay? So based on the silhouette, it's similar width and length of the plot, then it's a optimal number of clusters. Okay, so that's the general idea, okay, about silhouette plotting. Okay, then that's the first approach we discussed, k-means, okay, k-means. The second one we are going to learn is called hierarchical clustering. Okay, hierarchical clustering. So hierarchical clustering, it's based on, you can do some plot. The plot is called dendrogram plot. Okay, we are going to see it. Okay, dendrogram plotting. And what we will see, we call it agglomerative clustering. Okay, agglomerative clustering. So agglomerative clustering is we start with each sample as an individual cluster. Okay, so initially you have each sample is a cluster itself. Is a cluster. Okay, then we are going to try to merge them. You're going to try to merge, okay, based on some distance calculation. Okay, maybe then you have this two, and then you can merge this two. Okay, so that's, so you start with individual cluster, but then you're going to merge the closest pair of clusters. Okay, you can continue merge until there is only a single cluster remains. Okay, so that's called agglomerative clustering. Okay, it belongs to hierarchical clustering. And for the agglomerative hierarchical clustering, is it because you need to find the close sample points, is it? So same question, we need some distance matrix. Is it cluster distance? So how do we measure that? Is it? So there are a number of ways. One is called single link. Okay, what does that mean, single link? So you already have this cluster. Is it red cluster, yellow cluster, and the blue cluster? Is it? And within the cluster, different cluster, so this is a point and this is a point. These 2 points from different cluster. Is it? But the closest, is it this 2 points versus this 2 points? Is it this red and this yellow? Definitely the distance between these two is smaller than the other pair, is it? So these two are the 2 closest points between these 2 clusters, is it? So the single linkage is you will find all of the pairs between 2 different clusters and their distance, is it? And then you pick the smallest one, is it? So among these 3, is it? This is 1, this is 2, suppose this is 3, is it? And we can see between red and yellow, 1 is the minimum one, is it? 1 is the minimum one, so the idea here is, then I'm going to merge these 2 clusters together. Merge. Okay, because it's a hierarchical, is it? It's keep merge. Is it keep merge? So what you based on to merge in this case, it's called single link. Then you can merge them together. Okay, so that's regarding single link. The second link measure, is it? Distance measure, we call it complete. And the complete is the opposite of the closest point. You choose the furthest away, is it? So this point and this point is the furthest away between these 2 clusters. And assuming the next one may be this So suppose you have some other blue ones, is it? And this, is it? Suppose that's the 3 pair of the distance, is it? Within the furthest away pair of point, you pick the minimum one, is it? And then we find the closest one. Closest one. Closest one, then definitely it's blue and yellow, is it? Okay, it's blue and yellow, then I'm going to group blue and yellow, these 2 cluster together, is it? I'm going to merge these 2 together. Okay, so that's called complete. So based on the description of these 2, you can see the single linkage will lead to more chain distribution. Is it? It's a long chain can produce, is it? And with complete linkage, the cluster is more spherical, is it? It's more round, is it? Yeah, so that's the feature, okay, here. And here it shows some examples. Is it if you use single linkage, is it it's more chain, is it long? But if you use complete, it's more round. Is it more sphere distribution? Is it the same thing over here? Is it more sphere distribution versus this is more long chain distribution? Okay, so that's the idea about single linkage and complete linkage. Okay, so we already understand single linkage, complete linkage, and there are other distance measures. Okay, one is called average length. So what is average length? Average is between these 2 clusters. Is it you consider every pair of the distance. So average all pairwise distance. And then you find the closest one, and then you merge. You merge. Okay, that's called average. And the other method is called centroid. Centroid is what? So based on these 2 groups, suppose you have some other group, is it? You have some other group. And this is the centroid, this is centroid. And over here, you also have centroid, is it? And then based on this, so the centroid, these 2 are closest. So I'm going to merge these 2. Okay, so that's called centroid way. Okay, and the last one over here, this is called ward distance. Okay, ward method. Ward method is consider what? Consider merge 2 cluster. How does it change the total distance from the centroid? Okay, how does it change the total distance? Is it? So total distance when you merge, is it? So total distance from the centroid, so you plan to merge these 2. Is it? And this is the central. And then you need to consider the total distance versus the other one. Is it? Maybe over here you have the blue one, or we call green group. Is it? Green one. And then here is the centroid between the green one and the blue one, and the yellow one. Is it? So you are going to find the distance, is it? So this is total distance, is it? Total distance. And then you compare this group versus this merge, is it? Which one is smaller, is it? So suppose this is smaller. Then you are going to pick the merge of red and yellow. Okay, that's called the ward method. Okay. Okay, so those shows different cluster distance calculation. Okay, and there is a general formula, as it is called Lance-Williams algorithm. Okay, for the distance calculation. Then in this case, this single expression can be used for all we just discussed. Okay, but it's based on the coefficient. Is it alpha and beta and gamma? The coefficient, how does it define? Okay, so that's a very general expression regarding the distance. Okay, then let's take a look example. Okay, how do we group a class together in bottom-up fashion? This is hierarchical, the agglomerative. Is it agglomerative clustering? Hierarchical one. Is it? Okay, so here it gives us the data distribution. Is it? So it's so this data is very simple. Is it a student test or assignment marks? Is it student ID? Is it? Okay, you have the mark, and so that's the original data set. And from the original data set, we can come up with a matrix. We call it approximated matrix. For this approximate matrix, you have number of rows and number of columns. Is it? Both is with the student ID. Is it? And what? And each of this, is it? So what this shows is the distance between the data point 1, data point 2. Is it? So the distance between these two, I just use the offset of the two marks is 3. Is it 10 minus 3? Is it? Is 3. So of course it's symmetric. Okay, this matrix. Is it? And let's see, 1 and 3. The offset here is 18. Is it? Yeah, it is 18. 1 and 3. Is it? And 1 and 3. Is it? It's 18. Is it? So that's how this matrix come up. Okay. Once you have this matrix, proximate matrix, is it? And what you can do is you find the smallest one. So find smallest. Okay, smallest is between 1 and 2. Is it? That's why I merge 1 and 2. Is it? This is called a dendrogram. You're going to come up with the dendrogram for all of the samples. Okay, for all of the samples. Okay, after you merge 1 and 2, after I merge 1 and 2, then I'm going to shrink my data set looks like this. So this is a merge. So this is already a cluster. Is it? It has 1 and 2 points there. Is it? And the mark, I'm going to pick the maximum one. Okay, within this cluster, so it's 10. And next, the same thing, I'm going to come up with this approximate matrix. Is it? Approximate matrix, so this is 10. Between the first cluster and number 3, it's 18. Is it? It's 18. Is it? Between 1 and 4, it is 10. Is it? It is 10. We got this. Is it? And we come up with this new approximate matrix. The smallest one is what? It's 3 and 5. Is it? It's 7. Okay, so that's how you cluster these two. Is it? So we already cluster 1 and 2, 3 and 5. Is it? This dendrogram, is it? So the x-axis is your samples, and the y-axis is the approximate matrix distance. Is it? So I already merged these two, and you can continue doing something like this. Is it? Then you are going to have the first cluster and the point 4 group together. Is it? You continue this until there is a single cluster. Is it? You only have this single one left. Is it? So that's it. And then how do you determine the number of cluster? You don't want to just have a single cluster. That's not the purpose. So you can pick a cutoff distance. Suppose here I said, okay, I'm going to use distance of 12 as a cutoff point. So if you pick this cutoff, is it within this dendrogram? And you will say, okay, I'm going to have 2 clusters. Is it? So, okay, for this data set, then I'm going to have 2 clusters. That's how you make a determination about the number of clusters, okay. Okay, so that's the idea about a hierarchical clustering. And the last one is called DB scan. That DB scan is what is dense-based spatial clustering of applications with noise. Okay, so the name is quite long. So what is the idea over here is within the cluster, we have some special points. Okay, we have call points, and we have border point, and we also have noise point. So for each of the sample, you need to categorize it into this 3 type of point. Okay, and for dense-based, we need another parameter. This is the radius. Okay, radius and the minimum number of points. Okay, we still need this. And what's the definition for call points? Call points are defined as within the defined radius, epsilon, etc. And it has minimum points of neighbor points fall within this circle, is it? Then this point is considered as a call point, call point, okay. And what is a border point? A border point, is it? It has fewer than minimum number of neighbor points within that radius. Okay, like for this point. It doesn't, it only has 1 point fall within its radius. Oh, it has 2, it has this point and this point. Is it? It has only 2, but the minimum definition here is 3, is it? So that's why this point we define as border point. Okay, what is noise point? Noise point is within the defined radius. Is it has none of the other points fall within this circle. Is it within this sphere? Then it's called a noise point. Okay. So this is a concept about DB scan. Is it DB scan? So once you know the 3 points, is it then you define the clusters? Is it? Yeah. Okay, so that's all regarding the concept. Okay. And what next we will see is our examples. Okay. How all 3 going to be applied to our examples. Okay, the first we will start with k-means. With k-means, okay. And over here, the data set, we just use some function to generate a data set, okay. And this data set looks like this. And visually, it's clear. We can see there are 3 clusters. Is it visually? Is it? And how do we apply k-means? Okay. And for k-means, we can import k-means from the cluster package. Is it? And the k-means module. Okay. So we initiate the k-means module, and you specify the number of clusters. And this initial number, what it defines is you can run this algorithm 10 times independently, okay, but with random centroids to pick, okay, so that you can minimize the square of, or sum of the square of the error. That's the point, okay. And this maximum iteration defines the maximum number of iteration for your clustering to converge, is it? And this is you define certain tolerance value so that your iteration will converge, won't forever to go, is it? Okay, so this is, we are going to apply the k-means, is it, to it. Then we do fit and predict. We do training and predict, is it? After training and predict, we get the predicted value, is a corresponding predicted value. Then we can do the scattered plotting, okay, based on the predicted value, okay, using its two features, is it? Okay, then we have this kind of scattered plotting, is it? And we can also find their centroid, okay? And with sklearn, it also gives your centroid. So after sklearn, if you want to find the centroids point, you can call cluster centers, okay, cluster center. Then it will return you where the centroid is after the clustering. Okay, so this is a k-means, is it? And you remember regarding k-means, is it? We want to find the optimal number of clusters, is it, clusters? And previously we discussed the inertia in k-means, is it, in k-means? Inertia is regarding what is that within cluster sum of the square error, is there sum of the square error? Okay, and how do we collect the number of squares, or the number of clusters? So here we do like something like this. We use a loop, is it, a loop 10 times, is it? And so with 1 cluster, 2 clusters, 3 cluster to 10 cluster, is it? We are going to apply k-means plus plus, okay, k-mean plus plus, and then the similar number of tryouts, is it? And then you do fit, is it? And then you can find the inertia, is it? And we can append the inertia to this list, is it? Okay, and then, and oh, let's see. And then we can draw the distortion, is it, versus number of clusters, is it? So this is that sum of square of error, is it, sum of square of error? And you can clearly kind of see this is the elbow point, is it? It's kind of like our arm's elbow. That's why we call it elbow, is it? So after this, you can see the distortion doesn't decrease that much, is it? Not like the previous, the first two, is it? So it doesn't drop that much. So in this case, it's all 3 clusters will serve good, is it? So you, with this data distribution, is it, we can have 3 clusters. Okay, so that's the idea. Okay, that's the idea here. Okay, and the silhouette, is it, regarding the silhouette? And the silhouette is a measure of how similar object to its cluster, is it, to its cluster? And the value generally distributed between -1 to 1. Okay, and if your silhouette plot is pretty close to each other and also approach to 1, then that means the cluster ring is pretty good, okay? So let's see, how do we get this? So in sklearn, we can also do silhouette coefficient collection. Okay, so it belongs to the matrix. So over here, we still do k-means, is it, with 3 clusters, okay? And then we train our model, is it, train our model. And over here, you get the number of clusters, is it? Clusters we can get, is it? And how do we find each cluster's silhouette values, is it? You just call silhouette samples, is it? And then you plug in all of the feature values and the target values. This is a predicted one, okay? Be careful, this is a predicted target value. Target value, is it? And once we have those, then what we can do is you get all of the silhouette values, is it? And the silhouette belong to certain cluster, is it? Then I'm going to sort the values. Okay, sort the values. And then I'm going to do bar drawing with the values, silhouette values. Okay, do bar drawing. Okay, do bar drawing. And here it shows us the results, the bar drawing, is it? And we have 3 clusters. This is called silhouette. The silhouette coefficient, is it? And this is the corresponding cluster. Is it? Here we have 3 clusters, is it? So that's why we have these 3 different colors, is it? You can clearly see this 3 bar plotting. This is bar, is it? The 3 bar, the width and the length of the bar are very similar, is it? Are similar. And their bar is also pretty close to 1, is it? And this is the average value of the silhouette coefficient for all the 3. And from this silhouette plotting, you can clearly see it's very similar to each other, is it? So this is good clustering. Okay, good clustering. Okay, so that's regarding this silhouette. And then next we change it to 2 cluster, is it? If you change it to cluster for the silhouette, if you take a look, the silhouette, is it? And you can clearly see, is it, the width and the length are different, is it? Are different. So not a good clustering. Okay, so that's about the silhouette to determine the best number of clustering. Okay, we just have a couple of minutes, and let's see. So today we discussed the k-means. Is it the 3 clustering? 3 clustering algorithms, is it? So today's discussion is clustering. So let's ask some questions and get some bonus point. Okay. So is clustering supervised learning?
It's unsupervised learning.
Okay, very good. Okay, you can send your answer to the chat. Okay, so it's not, is it? It's unsupervised learning. Okay, unsupervised learning. Yeah, please send your to the chat. Unsupervised. Okay, and supervised learning previously we learned, is it? Let's just recall what we already learned. Do you still remember? Is it at the very beginning we learned perceptron and add a line? Is it add a line? And then we also learned logistic regression. Is it? And we also learned linear regression. And we also learn support vector machine. As a support vector machine. And then we also learn decision tree as it and random forests as it. And we also learned gradient descent is it. Is it? And any other ones that we learned? Who remembers? Pardon me?
KNN.
Oh, yeah, KN. Yeah, I almost forgot. Thank you very much. You can send to the chat, okay. KNN, is it? And these are, so among them, some of them are regarding what? Like logistic regression is about predictor value or about classification?
Linear regression is about prediction.
Yeah, very good. And how about logistic regression? Is it for prediction? Is logic?
Yes.
Think it hard. Is it
Okay.
is for classification? Is it? You remember it's for, even though there is a word called regression, is it? But here we use logistic regression to do classification. You remember, it's an improvement over add line, is it? Because you are not going to do that unit step function. Instead of unit step function, we do this kind of distribution, is it? And so that's about classification, is it? And support vector machine is also doing classification, is it? Yeah. So so that's just about prediction or classification, is it classification? And yesterday, what we learned is about ensemble learning, is it? And ensemble learning is like a random forest, basically also belongs to ensemble, is it? So you can combine multiple trees together, is it? Not just the ensemble, you can also use multiple learning models together, is it? And then we use majority voting, is it, to determine the results, is it? So that's regarding ensemble learning. So so that's basically all for today, okay? And tomorrow we can